Hi, this is Jeff Stravinsky, HPN SA Manager, and today we'll be walking through Networking 101. And today we'll be going through a few simple networking topics that will cover many simple basic terms and technologies that will set the basis for future talks. So as we start off here, one of the first things we want to review is the OSI protocol stack. The OSI 7-layer model is based upon differentiating different levels of communication into different layers. We're going to start off here with just the first 4. The physical layer, or layer 1. This actually defines electrical characteristics, cabling characteristics that define on how 2 or multiple devices can talk. This is typically defined at the base IEEE 802.3 level. And examples here would be fiber optic cabling, different types of copper cabling, whether it be category 5 or coax, defines electrical signals, how many amps, volts, what frequency, and it's really at a basic level. So for an example, at the Ethernet level, Ethernet generally today goes across Cat5 or Cat6 cables, so there'll be layer 1 specifications that talk about how that works, or it can run across fiber optic cable. Also the same thing as well, there'll be characteristics on how the Ethernet is transmitted. Now, at this level, we're really talking about bits and bytes being translated. At the layer 1 level, there is no addressing at all. So there's no concept of a device or another device. And typically, at least nowadays, layer 1 is typically point to point. Although in the past, it has been a point to multi-point protocol. Not really even a protocol, that wouldn't be correct saying it that way, but it was defined as being able, the electrical signal could be sent between from one device to many devices. And nowadays, it's usually one device to one device. As we move up in the layers, move to layer 2, which is also known as the data link layer. At this layer, we're actually starting to formulate actual real messages between devices. And those are typically called frames. The types of protocols that would be a good example to bring up as a layer 2 protocol would be Ethernet again, very popular. But when we get down to this level, we're actually talking about, like I said, messages being delivered from point A to point B. The messages are in a format that's called a frame, and those frames are typically sent with locally based addressing, meaning that the addressing is only good in a local manner. It's not good in a global manner, and we'll get into that later on as we talk through things. I did not mention that the type of equipment that's available in layer 1 would be cables, connectors, and then a device called a hub, which is kind of a historic device. In layer 2, we start to move into switches and bridges, would be the types of equipment that operate at layer 2. Then we move up to layer 3, and this is also called the network layer. And this is where we start to get into protocols that can interoperate at a global level, meaning that their addressing is based upon not only giving you the identity of a device, but also the identity of its location. Typically, the messaging format is called a packet, and typically the devices that move this traffic around are called routers. Now obviously there's multiple layers above this. Layer 4, the transport layer, Layer 5, the session layer, layer 6, the presentation layer, and layer 7, the application layer. We won't get into those in this talk. Now we'll move on to Ethernet topics. Okay, let's get into it a little bit here. Ethernet itself, like I mentioned, is a simple message. It's designed to be delivered at a local level, and it's very simple in its structure. And let's walk through it right here. So the first part of the Ethernet frame would be the destination address, and this is defined by utilizing what's called MAC addresses. MAC addresses are the burned-in address that is on every single Ethernet network card out there. It is, like I said, it's burned into the factory. It is typically made up of two parts. First part is an original unique identifier, and that's typically given out per manufacturer. And then after that identifier, the rest of the bits are actually utilized to identify the card. And usually typically the easiest way to define a MAC address really is to think of it as a serial number, and it's a unique serial number, and it's identifiable only to that Ethernet card that came out of that manufacturer. So the first address is the MAC destination. The second address will actually be the source MAC address that it came from. Then there is a relatively new set of tags that are out there that are called the 802.1q tags, and these are typically there to define actually the VLAN that this Ethernet frame is supposed to be a part of. Then the next part is the ether type section, and the ether type defines what the frame format looks like, meaning what fields are in what order. Typically nowadays, there's only one ether type that's utilized. That's normal. Back in the past, there actually was multiple different ether types that were available and were used simultaneously based upon whose upper layer protocols you had out there. The next part actually is the payload. Typically, the payload can be anywhere from 46 to 1500 bytes. But nowadays, we can actually go even larger than that with what we call jumbo frames. And then lastly, there is a CRC field, cycle redundancy check, which allows us to create a CRC for the payload itself, and therefore if there's anything corrupted, the CRC can immediately identify that there's corruption there within that frame. So let's dive into actually how a frame moves through our network. So going back into the past, when Ethernet was first developed, it was actually developed upon devices being connected through a single cabling system. And the way it worked was that a device, if it wanted to send a frame from one system to another one, what it would do first is actually listen on the wire, find out if anybody else was talking, because only one person could talk on the wire at one time. If no one was talking, it would actually then transmit that frame onto the cable. The cable would actually be interconnected to all the other systems in the network, and all systems would receive that frame. At the Ethernet card level, it would actually then look at the destination MAC address. If that destination MAC address matched that of its own MAC address, it would then take the frame and move it up towards the operating system. Very simple, very easy, not very complex, but not very scalable at all. Obviously, the big thing you notice is that only one device could transmit at a time. It was also a pain to cable up. Then came along the Ethernet hub, which actually simplified the cabling, but did not fix any of the scalability issues. You still only had essentially one Ethernet cable technically, with a certain amount of bandwidth available to it. And in the cable system and in the Ethernet hub system, the network itself, let's say the network cable or the network hub, did not have any intelligence, did not have the ability to decide whether two devices could talk to each other or not. It was very simple. Then came along the Ethernet bridge. We nowadays call it the Ethernet switch, but essentially it was a hardware device that actually understood the MAC addresses and could actually make decisions on whether or not two devices could talk to each other. And it also opened up the concept of the fact that frames could actually be stored and forwarded, and thus we could actually open up additional bandwidth and gain greater utilization of the network. So really what Ethernet switches allow is they allow us to forward frames very quick. They do it into hardware. It's very fast. They typically use application-specific integrated circuits, ASICs, to actually do that. They typically have what's called content addressable memory. That content addressable memory is a very fast lookup engine that is able to look up and figure out where destination MAC addresses are. So very simple as well in the way it works, but can actually be very complex based upon the size of the network or the amount of features that are turned on. And what we'll do is we'll go through here in the next slide and actually talk about how a switch actually does this. Okay, let's go through some very simple examples of how a switch works. Look at the slide that's up in front of us right now. It's got 4 devices on it. Devices A, B, C, and D. Each one of them has its own MAC address. And without getting into too deep of a technical discussion here, let's keep it really simple. Let's, for the most part, say that A wants to talk to C. So what will happen is that A will send out a Ethernet frame with the destination MAC address of C, which is 001A, 8C01, 3333, as an example. It'll put in its source address of 001A, 8C01, 1111. Okay, so what happens is that A transmits that frame out. The switch receives that frame on port E1, and what it then does is it actually, in its MAC address table, or in its oftentimes known as content addressable memory, CAM, it'll mark down that that MAC address is at that port. Now, initially, when the switch gets a destination MAC address that it's unaware of, what it'll then do is it'll actually forward that frame out every single port. So what it'll do is it'll take the frame that was sent, it'll send it up port E2, send it up port E3, and send it up port E4. All 3 of those devices, B, C, and D, will receive the frame. And if in the case of B and D, they're just going to ignore it, and nothing will happen. There'll be no messaging that'll go back and saying, you know, I'm not that person. They just receive the frame and they drop it on the floor. It's dropped on the floor at the device level. Now, when the switch sends it out E3, it actually will get received by device C. Now, assuming that device C is going to respond back to device A based upon whatever it's doing, it then will craft out an Ethernet frame with a destination MAC address of 001A, 8C01, 1111, with a source address of 001A, 8C01, 3333. Great! It sends that frame out, the switch received it, it says, aha, I now know where 001A, 8C01, 3333 is. It's out port E3. Great! So now, if device A sends another frame to device C, it'll be received by the switch, it'll look at the destination MAC address, it'll say, aha, I know where it's at out port E3, and it'll send it up port E3. It won't flood it out any longer. Now, of course, in the world of Ethernet, we've only been talking about one type of traffic, and that is point-to-point or unicast-based traffic, where a device is sending to another specific device. There's actually 2 different other types of traffic that we can have on an Ethernet network. The first one is a broadcast, and a broadcast is specifically a message from one device to many devices. So essentially, in that case, what happens is if device A wants to broadcast out to devices C, B, and D, all it has to do is send it to a MAC address of FF, 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 or essentially all Fs. The switch will receive it and it'll send it out all ports. So E2, E3, and E4 will receive the frame, and on top of it, their Ethernet network adapters will accept that frame and send it up to the operating system. So a little bit different than flooding. You know, flooding is receiving a unicast message and it's not meant for me, so I drop it. But in this case, everybody's Ethernet card will accept a frame from destined for all Fs. So the other type of traffic out there is one called a multicast. And a multicast is similar to a broadcast. Instead of going to everybody, it goes to a group of people or a subset of people, right? So multicast MAC addresses do have a set format. They are predefined, and a lot of different protocols use them. But essentially, what happens is that if it wants to send out a frame to a certain layer 2 Ethernet multicast address, it'll send out. The switch will receive it, and typically a very simple Ethernet switch will actually send that frame out and flood it out to all ports. It'll be received by all Ethernet adapters, and then those individual Ethernet adapters that they've been programmed to listen for that Ethernet MAC address, they'll also send it up to the operating system. There's a few more advanced topics I'm not going to get into in this talk, where the switch can actually be aware of the layer 2 multicast MAC address, and it can actually selectively send it to certain ports instead of all the ports. So those are the 3 different types of Ethernet frames you can send out and how an Ethernet switch will handle them. So there are a number of issues that can happen on layer 2 segments, specifically Ethernet segments. So I'll just hit upon a few of them here that are very common. So one of the most common problems that we can have in layer 2 networks is loops. And this would be whereas a packet it can have a route through a layer 2 based network, whereas it can be sent out one interface and make it go through a number of devices and actually make it all the way back to the same port that it was sent out. Or another way of maybe stating that might be that the network itself is circular, or it has multiple parallel links. One of the problems with layer 2 network protocols such as Ethernet is they do not have what's called a time to live. And why is that important? So TTL, we'll actually get to that a little bit later when we get to layer 3 protocols, essentially is a timer. And it says that if you send out a frame and you have a TTL field in it, what you can do is every time a network device touches that frame, you can actually decrement the TTL. And the nice thing about that is if a frame has a TTL, if it seems to be wandering aimlessly through the network, eventually its TTL will get decremented down to 0, and a device that receives a frame with a TTL of 0 will drop it. So it can certainly limit problems with frames that don't really have a real destination. So that's kind of an issue. And that specifically comes up when you have loops, because again, if you don't have TTLs and you have loops, you can have packets just endlessly going around in circles. Obviously, different types of traffic actually can really have some issues with loops and networks and the lack of TTL and Ethernet, and that would be broadcasts. So normally an Ethernet switch will actually forward out all of its ports a broadcast. And if you potentially have a loop-based network that has no loop control inside of it, broadcasts could get out of control and create what we call a broadcast storm. And that can obviously, create lots of issues within a network, i.e., eating up all potential bandwidth with broadcasts. As well, all devices typically listen to every broadcast they receive. So it even can affect operation at an Ethernet card level and at an operating system level. Of course, as well, depending upon if you have a network that's incorrectly constructed and you don't have the right features and control, you can actually learn about MAC addresses potentially being on the wrong interface during a loop situation, which means that switches can actually then think that a device changed places within the network when it really didn't, and can create further issues. One other really big thing is the fact that standard Ethernet does not typically have quality of service built into it. Now there has been additions to Ethernet, specifically 802.1p, that can actually allow us to mark packets, but it's very simplistic in nature. And then as well in standard Ethernet, there really isn't a good way to do segmentation. So there needs to be something that can be added onto that, and we'll be talking about that when we talk about 802.1q and VLANs. But standard Ethernet has all of these issues that we named here, and there's been a number of features that have been added on to Ethernet that fix these issues going forward. So to fix one of the inherent problems with Ethernet-based networks is a protocol called Spanning Tree, or also known as 802.1d by the IEEE community. What it does is it ensures a loop-free topology within the network by detecting and blocking redundant paths. It does this by forming a tree. And a tree, if you think about it, typically is a structure that does not have any loops. It has multiple paths from point A to point B, but it does not have any loops. So if you think about a tree, it has a trunk and then large branches and then going out to smaller branches, but never do any branches actually normally interconnect. What Spanning Tree does is it has the concept of selecting a root bridge, and from that root bridge the rest of the network topology is built in a manner that no bridge or switch actually loops back to another bridge or switch in a loop type fashion. When it does this, it actually calculates a least cost path from each bridge to the root port, and each one of those least cost paths from each segment becomes what's called a designated port, and then anything that is not a root port or a designated port is actually disabled, and we'll actually walk through this very simply here within a network diagram. Okay, let's review a really simple network. 2 network segments, 2 switches. Each network switch has a connection to each network segment. So if you look at the basic design here, there actually is a loop. A device at the top, 001A, 8C01, 1111, if it was to send out a broadcast onto segment A, it would be received by both switches, switch on the left, switch on the right. They would both forward that frame onto segment B, and then thus not only would the device at the bottom, 001A, 8C01, 22222, receive both those broadcasts, but as well each switch would also receive the broadcast that came from the other switch, and it would thus then repeat that broadcast back onto segment A, and then thus each switch would receive and transmit it back onto B, and thus unlimitedly until the end of time, or until the switch is melted. So what Spanning Tree actually does, like we mentioned, and I won't get into the actual details of how this works, but essentially the switches will go through an election process. One of them will decide to become the bridge. He will look at the network segments that he's connected to and the switches that are out there, and essentially build a least cost tree that can connect all network segments through all network switches. Essentially what will happen then is that in this case one of the links will actually have to be shut off to take out the loop, and that'll be the switch on the right, and it's link B, and therefore in that point we'll actually have a network that's loop free. Now, the way it works, without getting too detailed here, is that that link from the switch on the right to segment B actually isn't physically turned off. It's actually moved into a state in which it's only listening but not forwarding. And therefore, if the switch on the left, if it was to lose its connection to segment B because of a cable cut or a port going bad, the root bridge could then reconfigure the network and turn port B back into a forwarding state, thus allowing the network to keep on working. So it's very simple in nature and how this works. It really was designed back in the day when networks were very small and switches were very expensive. Well, actually, it was originally developed when there weren't even switches. There were actually only bridges. And bridges were back in the day of which a bridge typically only had 2 ports. So they're very simple networks that were not very big. They didn't have a lot of switches and they didn't have a lot of loops in them. So the calculations needed to remove loops were pretty simple. And that's a key point because as networks got bigger, spanning tree really did not scale very well. And we'll go through some problems here that you can have with spanning tree here on the next slide. Spanning tree's got a lot of issues. We won't get into all of them here or really get into them in any depth, but really the largest issue with spanning tree is the fact that it was designed 20 plus years ago when networks were much smaller, when a typical network might have only had 2, 3, 4 bridges inside of it. It was not designed for the size and complexity that we have today, and failure recovery can take minutes in many cases, and sometimes might not ever happen because the way spanning tree works. It's a very complex algorithm. It's difficult to troubleshoot. If you're in a large-scale network, it's very manual. It's really because the spanning tree itself doesn't have any standards-based tools built into it to help you troubleshoot. It's typically a very manual process in many cases on many people's networks. And the other thing as well too, there's a lot of failure scenarios where the algorithm can overload the switch processor. If the switch processor is not big enough, or if the operating system that's running inside the switch is not advanced enough to actually limit how much spanning tree takes up of processor utilization. So there's a lot of issues. Spanning tree, again, very old protocol that somehow has made it into 2011. We're all obviously all trying to get away from it, and we'll talk about that in future training sessions on what is changing and in the marketplace right now in terms of spanning tree. Let's move on to some other topics in the world of Ethernet. So the first topic, and most people have heard this term but may not exactly understand it, is the term VLAN, which also stands for virtual LANs. So obviously with large multi-port Ethernet switches, you really have the capability of having a lot of networks, a lot of network devices connected to a single device or a group of devices. And what VLANs allow you to do is carve up one physical switch into essentially multiple layer 2 Ethernet networks. In the past, if we needed to have, say, a network just for manufacturing, another one for the office, another one for operations, another one maybe for the IT group, you might actually have to deploy 4 Ethernet switches, one for each one of those groups. And what VLANs allow you to do is actually carve up an existing switch or virtualize it so that it actually acts like multiple switches. So inside of that switch, it's essentially what it's doing is dividing up the CAM table. So essentially on a certain VLAN, say VLAN 20, it's going to be made up of just a subset of the MAC addresses that are available in that switch. And if we have another VLAN 30, it'll be another subset of different ports on that switch with different MAC addresses. Essentially those devices work and act as if they're on their own layer 2 segment, or essentially their own Ethernet cable, so to speak. and they really cannot talk to devices that are on another VLAN directly. There are some ways to do that. We won't go through that right now, but essentially this now allows me to segment up my network very simply utilizing one switch. Okay, now that we have VLANs, how do we actually connect multiple switches to each other? So originally, when VLANs first came out, they really did nothing to help you out with interconnecting one switch to another switch. And of course, we'd have the same situation. We might have accounting in VLAN 20 and engineering in VLAN 30 on one switch, and then those same two VLANs on another switch. And initially, what we would actually have to do is manually configure a port on both switches in VLAN 20 and connect the two switches together, and then connect a port on each switch in VLAN 30, right? But potentially there's not that much bandwidth going between those two switches on those two VLANs to need two different Ethernet cables connecting those two switches together. And so what came out was the whole idea of what's called trunking. And trunking is the ability to actually have one network link between two devices, and the ability then to carry traffic from different VLANs across that one network link. And do it in a way that traffic does not commingle, still have separation, and we'll go through in a second here and show you how technically how that. To do this, what we had to do is actually modify the Ethernet frame, and you saw this a little bit earlier. I didn't get into it back then, but the Ethernet frame was modified so that there was an extra 4 bytes utilized to actually do VLAN tags. So that tag is then broken up into is actually 4 bytes long. 16 bits is designated as the VLAN protocol ID. Then we have 3 bits left over where we can mark priority, and then 1 bit left unused there, and then as in between, and then 12 bits used as a VLAN ID. What that actually then allows us to do is actually have up to 4,096 VLANs that can be represented by that tag, allowing us to essentially now what we're able to do is any frame that goes between two switches will actually have that tag added to it, and therefore when it as we mark and say that this frame is on this VLAN, it'll be marked, it'll go to the other switch, and then what that switch will do is then look up and see if there's a VLAN tag available, and which VLAN it should actually put that traffic onto. Jumping back to our diagram of two switches interconnected to each other, before there was actually two links that were connected to these two switches. Now we actually have the ability to just connect one link, and that'll actually transfer packets between for multiple VLANs between two switches. Like I said, we have the ability to actually do 4,096. That's what the 802.1q has been designed for. Now, a few things of note, just so you guys are aware: certain switches can only handle a certain number of VLANs. That's based upon memory that's inside the switch, or how. And as we said earlier, the memory that's used for MAC tables is called a CAM, and so different switches have different size CAM tables, and thus can only do, in some cases, certain numbers of VLANs as well as a certain number of MAC addresses. Okay, moving on from layer 2 to layer 3, we're going to have a brief discussion about IP. IP, also known as Internet Protocol, and sometimes also brought up as TCP/IP. Actually, oddly enough, TCP stands for Transmission Control Protocol, and it is a layer 4 protocol that runs on top of IP. Oddly enough, there is also another layer 4 protocol on top of IP called UDP, or User Datagram Protocol. It's really more accurate when we're talking about layer 3 to just talk about IP or Internet Protocol. But as mentioned before, this is a layer 3 protocol. It has global based addressing, meaning that part of the addressing is actually there to designate what network or a geographic potential location, and the user side, whose the user address is. And essentially it's an addressing protocol that it's widely used. It's global or intergalactic in nature. It's extremely scalable. And here in front of you is just an example of what the IP header format looks like. You'll see here that is dramatically larger than the Ethernet frame format that we saw earlier. There's a number of other things that are brought up to enable different features. Now, one thing I want to mention here, because of the audience that I'm talking to, is that everything here is based upon layers. So at a electrical layer, there's a certain amount of bits that start off an electrical signal that designate that we're actually sending some traffic. Then after that, it's made up of the Ethernet frame itself. So you'll see the destination MAC, source MAC, CRC, and then within the data portion of the Ethernet frame, you will then start off the IP header. All right. So the IP header then has, in this case, the version, the IHL, the type of service, the total length of the IP packet itself, some identification frames, some flags, an offset in case the IP packet has been fragmented, and this offset will tell us where we are within the fragment. Time to live, which I mentioned earlier, is a more advanced way of ensuring that packets or frames, in this case a packet, only lives so long on the network. What upper layer protocol is this IP packet has, and I mentioned two already, TCP and UDP. A checksum just for the header, then the source IP address, the destination IP address, some IP options, some padding, and then finally the actual data. So a lot more options that are based upon here, and we'll start to walk through some of the other aspects in terms of IP packets here as we move forward. In networks today, there are devices that are called routers. You will also sometimes hear the term layer 3 switch. But essentially those are the same types of devices. In a layer 3 switch or router, what it does is it actually moves packets from one port to another one based upon the IP address only. Similar in function to essentially a switch, if you think about it that way, that a switch receives a frame, looks at the destination frame, and figures out what port to forward that frame out to, but based only on Ethernet MAC address, which is local. In terms of if we're looking at a router which does it at IP, it actually can do a few more advanced things. One of the things that we don't do in routers is we do not flood interfaces like we do in Ethernet switches. So if there is an unknown destination, that there actually is some rules that can be defined inside the router as to what to do if you have an unknown destination. If the destination doesn't exist, it can actually literally drop the packet and put it into the bit bucket. But as well, you can actually define what's called a default route. And I think most people in this call will recognize that terminology. And that default route says that, hey, if I don't have reachability to a certain IP address from this router, go ahead and send it this way as my gateway of last resort, or my router of last resort. Routers have what's called routing tables, and those routing tables essentially define where to find things inside the network. One of the interesting things about routers is that you can manually configure where to send traffic and where routes are, and as well you can have that automatically figured out. As well, A little bit different than an Ethernet switch. The Ethernet switch typically is saying, hey, I have a destination, I have to send this packet to, it's out this interface. What it is, it forwards it out to that interface, onto that network. A router, instead of forwarding the traffic out onto a network, it can actually take the traffic and send it towards another router. So we have a lot more specificity that we can have as to where we send traffic or whether we don't send traffic. Routers can make decisions, like I mentioned, either based upon routes being manipulated to a router, but they can also do it dynamically based upon what we call a routing protocol. And a routing protocol, what it does is it is a way that routers can exchange reachability to different IP networks with other routers. Some of the examples would be OSPF, ISIS, BGP, RIP. These are all just routing protocols that exchange routing information between routers. They actually don't, technically, these protocols don't route packets, they just exchange routing information. And then the router itself can either have automatic or manual rules internally to itself as to saying, well, which routing information should I value over what other routing information? So it can actually get fairly complex, or in many cases, a lot of routers default to very automatic assumptions as to how they should actually route their packets. IP routers actually have great tools in there for loop prevention versus the tools that we just talked about as far as Ethernet switches goes. So the first thing I mentioned previously is this concept called TTL, or time to live. IP, built into IP is this ability to actually do a countdown of how many times a network routing device has actually touched a IP packet. So the rules are for IP is that every time a router forwards a packet, it'll actually decrement the TTL down one number. And essentially, if a router receives a packet that actually has a TTL of 0, it actually will not forward that packet at all and dump it in the bit bucket. Obviously, this helps us if there's a loop and a packet is just going in loops around the network, or it actually helps us if there's very large-scale networks with very odd paths that actually are not taking packets in their most efficient way. So that helps considerably with loop prevention. As well, many routing protocols also have built-in loop protection. One of the routing protocols I mentioned briefly earlier was something called OSPF, or Open Shortest Path First. And OSPF is actually an algorithm that creates a topology automatically of the network for itself. And it actually has a set of strict rules that designate how traffic should pass from one network to another through multiple routers, thus ensuring a loop-free topology. Layer 3 has a lot of great advantages. One of the first things that it has as an advantage is it segments broadcast domains. And what do I mean by that? Typically, a lot of protocols are all actually based upon the broadcasting or the multicasting of requests or updates between each other. And lots of great examples here. So one great example would be the way that a layer 2 device, a layer 3 device discovers someone's layer 2 address on an Ethernet networks. There's a technology called ARP, or Address Resolution Protocol, but essentially it's a broadcast-based protocol. Anytime a device that wants to figure out another device's layer 2 address, but it knows its layer 3 address, it does an ARP, which is a broadcast. That means that everybody hears it. Obviously, as the network gets larger and larger and larger, there's a lot more ARPs, and therefore a lot of devices are listening to unnecessary traffic. There's other protocols like NetBIOS, AppleTalk, so on and so forth, that actually use broadcasts as a way of discovering other devices. One rule that we have for routers is that routers do not forward layer 2 broadcasts. So we actually can keep those broadcast domains smaller and therefore give us better scalability. It also segments spanning tree domains. Again, we don't want spanning tree to be too large. We don't want VLANs to be too large, and therefore we can actually keep them small but still provide connectivity for applications between those devices using a router. Obviously, one of the advantages of routers is they scale to build very large networks. The internet today is getting into the billions of devices that are out there. There's absolutely no way that an Ethernet switch or a series of switches with spanning tree and MAC table lookups could scale to that size. Layer 3 has great troubleshooting tools. One of the most well-known tools out there is ICMP. A very popular tool that uses ICMP is one called Ping. Another one's called Traceroute that allow us to actually check connectivity and routes between devices. And failure and recovery can be very fast. Layer 3 routing protocols were designed to understand the topology of the network a lot better, figure out and utilize loops, and actually have the ability to have multiple links between devices and still recover very cleanly and fastly. Quality of service, also known as QoS. QoS is a really big topic, and we're only going to hit upon it very lightly in this Networking 101 topic. There are actually multiple different types of QoS. Saying the word QoS does not mean one thing at all. But let's hit upon the two most likely areas that you will hit upon QoS as you deal with our customers. So there actually is a level of QoS for Layer 2 Ethernet-based networks. It's called 802.1p. Essentially, this is a way to mark packets, and you can mark them with essentially labeling them so that one is known whether or not that packet should be a high priority, low priority, maybe it has no priority at all. And essentially, like I said, it's essentially a way of marking a packet, but devices still have to act on the marking for there to be a QoS. So even if you have a device that actually marks a level of QoS, say high, other devices actually have to recognize that marking and act upon it as necessary. But typically, the types of devices that will act upon and recognize 802.1p are going to be Ethernet switches. And what that's going to do is when a Ethernet frame is marked, say with a higher label, the Ethernet switch itself will actually attempt to forward that traffic out before it forwards out other traffic to keep things very simple. QoS can also be implemented at Layer 3. There's actually two different ways that right now that packets can be labeled. They can be labeled using a technique called DSCP, or they can be labeled with a technology called type of service, TOS. They actually both utilize the same fields. TOS is a little bit older, has limited numbers of labels. DSCP is a little bit newer and has a higher number of labels. But essentially both are ability to actually mark packets. Now, compare and contrast this to 802.1p. 802.1p only works on Ethernet, only works on the Layer 2 side. So what it means that if I mark a packet with 802.1p, as soon as it hits a router, that router does not necessarily pass that 802.1p marking onto another network. By doing it with TOS or with DSCP, the router can actually forward that packet with those bits intact, so that a packet can actually go from one side of the network to another side of the network with that marking on it. Now that we have the packets marked, there are a lot of QoS techniques and what you do with packets. And again, way beyond the goal of this talk right here, but we can categorize them into the classification of packets, and then the ability to actually put them into queues and buffers inside of a router or a layer 3 switch, so that we can essentially then affect those packets with different policies. We might send out certain packets before other packets in the queue. We might give packets only a certain amount of bandwidth, either on a utilization level or on a packets per second level. We actually might even decide to drop packets based upon, well, either congestion inside of the router, meaning that I don't have enough bandwidth to send everything I have, or, and this gets to become very advanced, but I also have the ability to drop packets as a way of signaling back to an application to slow down and to stop sending me packets so quickly. So QoS is a really big topic, but just be aware that there are ways of doing it at both layer 2 and at layer 3. QoS, when you're asked if your device does QoS, the next question has to be back, well, what do you mean by QoS? Because there's so many different ways that QoS can be implemented. Access control lists, also known as ACLs. Access control lists, also maybe known as a filter, is a simple stateless security policy that's enabled on a Ethernet switch or a router. When implemented on an Ethernet switch, especially a layer 2 Ethernet switch, the access control list can be based upon an Ethernet MAC destination or source, and being able to either permit or deny two devices talking to each other. If implemented on a router, we can actually permit or deny either based upon a source or destination IP address, or based upon a port number. And we haven't discussed port numbers yet, but a port number is an upper layer protocol. So this would be at layer 4, 5, 6, or 7. Typically though, routers will only do this at layers 4 and 5, which of course we will get to in future instances, but to kind of preview that a little bit, layer 4 would say that two devices can either talk or not talk to each other based upon either TCP or UDP. And then if we move to layer 5, this is where protocols like FTP or HTTP are actually defined. And so a router could actually say, hey, these two devices can talk to each other on HTTP, but they can't use FTP to talk to each other. Essentially, it's a simple ordered list, meaning that I can actually have multiple filters defined in an ACL. The first one might say, deny, HTTP between these two devices, deny HTTP between these two devices, or between these networks, and then move on to FTP and then other things. And you can change up the IP addresses or the networks defined or the protocols defined, and then typically then at the end of an ACL you will then have a permit statement that will say, well, deny all these other things and then finally permit anything else that you haven't denied. And of course order does matter. Obviously if you did a permit first and then a deny second, it would actually hit the first rule that fit, in this case a permit, and then never get to the deny statement. So, and as well, these are applied inbound or outbound on an interface. So traffic coming into a router, I could do an ACL on, or traffic leaving a router, I could do an ACL on. So I have a lot of flexibility. But one thing that's really important here is that typically ACLs are stateless, meaning that they don't understand, everything about the traffic flow and whether or not traffic has flowed through an ACL before and is maybe potentially coming back. Anyway, that's a very complex topic. We won't get into it. This is all for this Networking 101 topic. We wanted just to hit upon some very high-level things at the lower levels of the OSI model to prep you for future talks that we will have. So thanks again for your time. And again, this is Jeff Serbinsky, HPN SA Manager. Looking forward to talking to you guys more in the future. Thank you. Bye-bye.